My name is Rado, and I'm going to talk today about protocol buffers, gRPC, and our use case for version technology agnostic protocol. So first, while I'm figuring this out, can you guys show me how many of you actually heard of protocol buffers or used them? 1, 2, 3, 4. Good. That's good. Hopefully there'll be something new as well for you here. For the rest, let's dig in. First, a little bit about myself. These are my social media and email. You can find me on that if you want to have a chat about anything in the presentation or anything else. I graduated in Edinburgh in AI and computer science. After that, my first job is in London, in an investment bank. But I decided to move back to Skopje, Bulgaria, and I started as a senior .NET developer at Macedonia. Now, I think currently I'm a team lead, have different projects around .NET and Python. I'm quite, how to say, technology not religious, if you can put it that way. I think every technology is great for some purpose or another. And my interest outside of work is usually around financial technology, but for those of you out there, I don't want to offend anyone, but I'm not a crypto fan, or at least not a cryptocurrency fan. There's a lot of reasons for that. I won't go into them. AI, I think that's our future, and I think in the next years we'll see a lot of improvements in that area, and they will start impacting our lives in different ways. And the funniest fact, I guess, or the most interesting fact about myself was I used to be a professional ballroom dancer. Now, you can't tell that now probably, but I used to be quite good. I even taught it at St. Andrews and their ballroom dancing society. Anyway, enough about me. This is going to be a brief introduction of what protocol buffer actually is, what gRPC is. gRPC is built on something that I hope you've all heard about. It's the HTTP2 that has come up in 2015. So we'll talk briefly about that in the future. And I'm going to also introduce our case and our project of why we decided to use protocol buffers and essentially gRPC. Right, then we'll have a Q&A. So protocol buffers was invented sometimes, I don't know, in 2000s by Google. Essentially, Google had a very interesting problem. They have loads of index servers because they keep, the entire internet cached, and they analyze it, target, the page rank algorithm and all. And as these servers grew by size and what they do, they started having these type of code all across their different server code. The different servers had to try to talk to each other, try to do requests and responses, but obviously the needs of these servers changed. So they started to have is like, okay, for this version of the protocol I'm going to do this, and then if it's the next version I'm going to do that, and it was really, really hard to keep up with the backward compatibility. So what essentially they did, well, hired better interns, I guess. So they had to solve the problem of, okay, what happens when technology moves on? If I change my code to be from C# to Java or something, do I keep classes again and rewrite the entire protocol in that new language? What do I do? Do I have to, upgrade or have a separate instance for every service that I keep up? What should be the answer? And essentially, they created protocol buffers. Protocol buffers is a specific language that describes exactly what you want to talk about to another service, and what does that service want to reply back to you that has backward compatibility built in. So hopefully that's got you intrigued, and we can actually see how that language looks like. All the ProtoBuf files are actually built in something that's a TXT file really, but with the Proto extension at the end. And let's imagine for a little bit that we want to build a phone book exchange services, whatever. So we're going to ask a server to tell you about the phone numbers of a person. So primary goal is to do the phone, so obviously you have to know what type of phone you're going to ask about or something like this, so we can create an enum type, and the way you specified in the protocol is something like this, quite simple. Here's where it gets interesting, because a phone number is meaningless to any of you unless you actually have it. So unlike any other data type of sending over the wire, you're not really sure whether it will be there or not. But here you can have the word required that essentially will enforce that every time you get this message, you will have a value there. Otherwise, of course, you will not be able to send the message across, which is fantastic. And obviously, you can have an optional value of what type the phone is, phone number, and have a default. Now, we'll talk a little bit about that more detail in a bit, but I just want to point your attention to the fact that you have a default value. Now, this, when you actually get to serialize this, to send it over the wire, if this is not there, it doesn't get put in the message. So it's not like your common serializer that goes from an object to a JSON message and just sticks something there and sends it because it has to be there. Actually, the compiler, the parser on the other side fills that value in because it's using the same proto definition, so which leads to great optimization. Anyway, so finally you can have a message of person that actually incorporates all of these together, and you can define things like IDs, emails, etc., and a repeated field of phone numbers, so you can send more than one. So actually, protocol buffers comes with something very important, and that's you can compile or, I don't know, transfer these definitions into your language, the one that you're most likely to use. C++, anyone? No? Okay. No, it's like, it has a wide range of languages covered. So what it will do, it will say, I don't know, I'll run the compiler, and out of these definitions, I actually get a C# classes that I can use within my code. I can also have Go, Java, Python, Dart, whatever you want. What does that mean? That means that before I send the message, I know what the message is going to be. I know what I'm going to have to understand, speak, and it will be as code within my code base. So, and I think that makes it the best DTO. And you might not be convinced yet, but let me try and do that, and convince you. Google currently uses around 48,000 of these for their internal service communication, and that's a lot. So, why? Well, I think if so far you haven't really been convinced, let me put out some of the highlights to you. So, because of the way that protocol buffers get encrypted into binary, it's essentially a binary thing that goes over the wire. But unlike JSON, these optional keywords and the default values allow you to actually reduce the size of the things that you send over the wire. I think there's something around, 10 billion of these get sent every second at Google. So imagine how much you would save if you can reduce the size of your payload 3 to 10 times. Now, of course, it's actually faster. Why is it faster? Well, actually, binary is very good for numbers, as you all know. This means that, things that slows maybe JSON parsers the most is actually if you send floats, if you send integers, or anything that is actually numeric. So if your data is numeric heavy, you should probably try out protocol buffers because against like common parsers, they can be 20 to 100 times faster in terms of speed, how you actually get access to your data. And there's more. It's the fact that you have a separate definition that can be translated in your favorite language actually means that it's easy to read. It's like a text description. Of course, it looks a lot like code, but it's still separate things. And you can actually enforce some of your logic of the service within the protocol. So it's kind of like this middleman person who will tell you, well, if you don't tell me your phone number, you might as well send me the message. I mean, we've all been there where you parse something, JSON, and you think, oh, of course, this value is going to be in the key values, but it's not there, and you get an exception, you have to deal with it, and here you simply won't. So I personally think that's fantastic. Less no exceptions, right? So microservices, obviously that was the birthplace of ProtoBuf. So I personally think that anything that you have to do in between microservices architecture or like any type of reporting or communication, that's great. Why is it great? Well, it's because you can substitute any of the microservice. You can plug a Go architecture or a Go type of microservice because, I don't know, you need asynchronicity that is on steroids. So just stick it out, stick the old Java or C# microservice, put the new one, and you actually don't have to think about how you get the data because the data will be the same. You already know what the data will be because the compiler will put it on in a Go code. So you straight go and use it with the access modifiers. So obviously that's a great use case. And lastly, but not least, definitely, gRPC is built on it, and we'll see what that is exactly in a bit and how it gives you an advantage. Now it's not all flowers, as they say. Unlike JSON, which is fantastic because you can look at it and see, yeah, that makes sense, it's a string. Okay, I don't think that was for me. But essentially it's like a QR code that doesn't make absolutely no sense to anyone because after the serializer finishes with it, it doesn't have a human readable form at all. It's just bits and bytes. So you don't. It's very tough actually. If you want to use Postman or Wireshark, you have to download a particular plugin for it or use a JSON proxy or whatever. So it's not the best thing maybe for debugging, but it's very good for the machine to understand it. So another minus that people have experienced is that the generated code, for example, let's say in C#, is not extendable. You cannot probably inherit it. You cannot do something with it, and it's kind of funky if you put functionality inside. You might be tempted. Don't do it next time you regenerate the definition from the external ProtoBuf compiler. You'll lose that. So it's not great. Not that you probably should keep any functionality in your DTO definitions, but hey. So it's also really bad for the type of data. Now, a lot of these comparisons were also done with XML. And because obviously that was the holy grail of transferring data in between things. And you know, if your data structure is very nested in, if it's very kind of marked up with tags or whatever, it would be really tough to do with ProtoBuf. Or let's say you just write like close nested definitions, and at the end of the day you realize just use XML and well, your hated XML parsers, or at least I used to hate them. Right, and I guess something that kind of came up as well when we started using it as well was people just went and said, but do we really need it? What's wrong with JSON? It's like, it's great, you can stick anything inside of it. Well, I mean, my personal view is, you know, you ain't gonna need it as a great principle, but maybe if you think that it's not important what the data contract, the thing you transfer is, and whether it's there or not, maybe you should reevaluate things, because actually this gives you great certainty. It's a contract. It's a contract. That's why you have Swagger on the other like things that allow you to version and explain to people what exactly goes in here. What do I want from you to actually think that you're asking me a valid question, right? So they can give you a response. So gRPC essentially was something that Google said, okay, that's great, but you know, how do we solve another problem, which was how can I invoke something on the other service over the wire without, you know, have the failings of like SOAP or some of the other well-known tools out there. So they decided that they'll do gRPC, and you might think that G stands for Google. It doesn't. Obviously, it stands for glorious green and some other stuff you can read on their GitHub page. But essentially, they said, okay, so we're going to extend this ProtoBuf definition language and put something like this. We're going to be able to define a service that I'll say what the request is going to be and what the response is going to be. And whenever you call it, you're always going to get that. And whenever you call it, you need to provide me what I'm expecting you to give me. So essentially, it's a really simplified way of doing a remote procedure call. And you've seen the messages as well. But it doesn't stop there. Actually, the feature of gRPC is great because it introduces something called streaming. And that means essentially you can give an endless amount of something. Like if I say hi to you, every one of you can return me highs. Because it's a stream of highs. In the other way around, if you look at it, you can send me loads of highs, and obviously I'll just say hi back. So, and it can be do a multiplexing where it can stream both ways. Now, actually, when you look at that last one, this looks a lot like I don't know, real-time communication. And the only difference, obviously, is that here I know exactly what I'm getting and what I'm receiving. It's not an arbitrary thing, and we both have the same understanding of what that is before we even send it, before we even begin communicating. One of the greatest features, I think, of gRPC, and that comes actually out of ProtoBuf as well, was that you can actually define what type of a message you have. And because of different cases, different logics, this might be different things. I might be in a good mode and just say hi, but I might be in a bad mode and just say, I'm going to send you a rude greeting. And the fact is, from whichever technology interprets that, will build you the automatic function of you always knowing the type of things that you're getting now. So you can like build in a very good separated logic to be dealt with the different types, generic logic to deal with the different types, which is, I think, fantastic. Now, there was a problem though. The thing about streaming is that it's not easily supported or not default supported in the internet. Now, I'll take you on a trip back in time, and you know, HTTP 1.1 was invented in 1999. That was 20 years ago, and I'm sure someone here wasn't born at the time. No? Great, thank you. That joke would have been not horrible if you were not here. Yeah, so you know, and it's obviously been a tremendous, fantastic success, but it's not good enough. So what the guys from actually, it was a lot of employees from Google that were part of the work group that came into it, said, okay, we need to rethink this. Why did they do that? So this is from a great book I read on internet networks. It's called Top Layered Approach to Networks. And essentially just gives you like how our internet works in like a image. You know, you have the application layer where it's like your browser or your application that does something and wants to send information. You have the transport layer where you have your TCP, UDP, depending on what type of data you want to point out or utilize. And obviously in the network layer where it's AIPs, that's why you have like, you know, different types of algorithms that find the shortest routes. The links layer is, you know, switches which have MAC addresses and know where to find whom so that you can actually get your packets around. And you know, those physical layer and the fiber optic that allows you to download in the content stream cases. So, but that's what happens over the wire. And HTTP essentially went and said, well, I'm an application protocol that is built on TCP, but I use TCP weirdly. What do I mean? Well, it goes and says, okay, I'll do a handshake to establish the TCP connection, because the underlying, obviously, transportation is TCP. And every time HTTP wants to actually do something, it goes and says, get me this, post me that, update that. So, the put or whatever. And it's like, but, okay, so every time I do a get, I have to wait for the response and then do it again to get my other thing. So, people were like, well, wait, let's rethink this. Why do we do it in this way? Do I really have to wait for my resource before I ask for the next one? So they went and said, no, let's build in multiplexing into HTTP. And they created HTTP2. And as you can see, the biggest difference there is the fact that once you do an initial GET request of, I don't know, your CSS or your JavaScript, you can actually do them in one go. You don't have to wait for the response. You can straight ask for it and you get it in much quicker. Because now the servers can understand that you send in multiple requests and gives you multiple answers. Now I know it's after lunch, so I decided I have to put this in. So if multiplexing is too complicated, maybe this will help you remember it. It's the same thing. We had a buffet, so we had everything together. That was quite cool, wasn't it? imagine us, all of us sitting there and be like, can I order like my salad thing and my name and some drink? So yeah, this is what they did essentially. And this essentially HTTP2 has some shortcomings because it's oh wait, I have another slide. Oh yeah, this one. So no IT conference is complete without waterfalls, and this is actually how your network is going to look like if you start using HTTP2. And as you can see, the improvement is quite clear. This actually stays at the bottom. I think it's unreadable for you guys, but it's twice as fast for that many resources on your web page. Right, so people went and said, that's fantastic. If I use this new HTTP2, I'll cut my time into, but actually the throughput of the network is also reduced because unlike HTTP 1.1, where you can actually log into a server and type, get me this resource, it will actually do it. It is a text protocol. All the commands in HTTP2 are actually binary, and so it's a much more efficient way of storing your protocol requests. It had to be backward compatible to HTTP 1, so a lot of the things that people hoped that would change, like better enforced encryption on all of your payloads, didn't actually do that to keep that. And the same with security of cookies, it hasn't really changed. So you will not really experience any improvements in other aspects of the protocol. So to tie it back to gRPC, essentially you can still use gRPC in a weird way if you use HTTP 1. Actually, that's what we used because back, I think it was a year and a half ago, a lot of browsers still didn't fully support HTTP 2. So we kind of used it in this real old way where you just use the remote service call and you couldn't really use any of the streaming features. So we had to resend things again if we wanted to make a new call, let's say. Right, so why did we decide to use protocol buffers and gRPC? Essentially, we had to build a game platform. But the game platform had many different games, services, and things that it had to do, all of them very specific. So we sat down and wrote the things that it had to do, and we end up with this like huge communication kind of layer that will have all of our data going across the client and the server to many clients that will have to get the same thing. And we simply said, okay, once this grows, if someone changes one thing, then a lot of things will have to change because we have the type of architecture with microservices. So we really sat down and said, okay, so this has to be optimal. This has to, be as small as possible because we're going to send it to a lot of people. And at the same time, it has to be, fast, robust, and impose some rules. So actually, it fitted the box quite well. So at the end of the project, what we had was, 100 of these or more, these small DTOs. We had 25 plus, I think, RPC services that were calling between the front and back end and the microservices themselves. So we had, this is just for context really, we had for responsive front-end applications that were doing different things, but they were always using the same definitions to do that. And we obviously also had, for microservices, as I mentioned, we had 30 IPs, something that was quite cool. When you machine generate your using Swagger or something else, your IP definitions, and you kind of pass these around between team members, and you go like, oh yeah, just read what it is. ProtoBuf actually allows you to go and say, well, inside the code base there is a file. I compiled it or put it there with the ProtoBuf compiler. Now you can, read it and just use it, and that's what you're going to send me. We put a middle layer in our APIs that was obviously doing the, as you would with JSON, doing the serialization for you. So we actually only work with objects, which is quite cool, which is great actually. So we kind of removed the need, and if you obviously ever need to access our APIs, We just give you the code to do it, you just fill it in. So, but with the data types and everything, hopefully you're using a type language, and it matters. Right, so we also did something that we thought quite cool. We put all of our communication data in NuGet server and essentially became an external package to the project. And what this meant is that every time the logic changes, we actually incremented the version of that. So it kind of became like as normal service, as normal library, as a normal thing that as it changes, it enforces new logic to you. So you just upgrade it and you change your code and it became much cleaner. It also actually removes your machine-generated classes that the compiler of ProtoBuf will do. You know, as any machine-generated code looks quite ugly. Right, so I think that's it. And I hope you enjoyed that. And if you have any questions, you can ask me. Oh.
Hi. After listening to all the presentation, I don't understand the part where you say it's backward compatible. So you have many servers, and if something changes, how the ProtoBuf and gRPC, ProtoBuf.
Yes, basically. So I'll go back. Essentially, it comes with the way that you define it. So if you look at this, you see the index numbers next to the fields. And what ProtoBuf says is, if you apply some rules, if you want to do a backward compatible protocol, all you have to do is delete, I don't know, maybe let's say the ID is no longer required on the right? You would say, okay, I want to add something else. So you delete the number 2, and it never exists anymore. But when you add something, you don't add it at the place of 2, but you add it after the 4. You add it as a new thing. So now what ProtoBuf will do is every time you make that request, it will automatically know that it no longer supports 2. And if someone puts something on 2, it will ignore it. So the way that the payload is serialized before you send it to someone, it will ignore it. And that's how you keep the backward compatibility. So even if someone tries to do something and thinks that does something, you essentially the server will say, hey, I don't need that anymore. I don't support that version. So that's how it keeps it backward compatible. Because unlike you can have the case where if you rely on that number, your code might break. But the protocol remains aware that at some point in time there was something in 2. So it will still probably give you an access modifier. It will not give you an exception that this never was there. It will know that it was there because it understands the indices, but it will not break, which is, hence,